Okay, so welcome everybody to the last day of Maine, the last day of scientific presentation, I should say. My name is Guillaume Lajoie. I'll be the chair for this morning's session. And just wanted to make a little announcement, slight change in the schedule. So we'll be swapping the two keynotes today. So the keynote this morning, just before lunch break, is going to be given by Laura Driscoll. I should say just before the panel discussion. And then Eva Dyer is going to give the final talk. There's some delays in flights, unfortunately. So that's that. That's about this. A little reminder that this evening there's going to be a party. So Karim, who's running a little late, is going to tell us a bit more about that coming forward. Right. So to kick things off this morning, we have none other than our own Patrick Mineault, who's joining us from New York City. Patrick is kind of a staple presence in neuro AI, both internationally and in Montreal. He's been acting on many, many fronts, and he's been kind of keeping tabs at a high level of how the field is evolving. And his opinion and position is quite useful and actually very valuable for all of us. And so today he's going to talk to us a little bit about bird's eye view of where neuro AI and foundation models are going. And so it's my pleasure to welcome Patrick to open up the day. Please join me.
Et voilà, et voilà, bon. Mon microphone, il est comme un peu fort parce qu'on dirait que je m'entends respirer. Ça. C'est un peu intense. Merci Guillaume pour la présentation. Je vais juste allumer ça pendant qu'il baisse ça. This whole thing will be in French, by the way, so it's going to be great. Ouais, c'est bon? All right, well, thanks for having me. It's great to be back. I really desperately needed to come back to Montreal, actually, because I really do need a haircut. My hairdresser is here. I've been to, this is like, I think my third time at Maine now. And plus I was an attendee before, so I guess that you've all seen me in many circumstances before. So my background is I did computational neuroscience vision at McGill, and then I moved to the dark side of industry. I was a data scientist at Google. I worked on brain-computer interfaces. I started a little nonprofit, which is called Neuromatch, which gives education and neuroscience and AI. I was most recently at Mineault, which you all know about, and now I'm actually in New York City at the Amaranth Foundation, working on a project on neuro AI safety. This is where my office is. It's pretty awesome. You should all come visit me if you're ever in town in New York. That's an open invitation. Just send me an email. And what the Amaranth Foundation does is it funds ambitious research in longevity and in neuroscience. They've been very active in the field of focused research organizations. So if you haven't heard of FROs, there's this idea that maybe between academia and industry, there's maybe a third thing that is neither academia or industry. And I really like that personally because I never fit in any particular box. So an FRO is basically a large-scale effort within a tightly coordinated, focused team that produces public goods and not private returns. So we've been active, amongst other things, in funding the Enigma project at Stanford University, which is a quest to decrypt the neural code. E11 Bio, which is building new tools for connectomes, as well as Forest Neurotech, which is building a whole brain functional ultrasound to be able to monitor non-invasively the entire brain. All right, so that was my pitch for the Amaranth Foundation. So now let's move on to the actual content of the presentation, which is about foundation models. Karim asked me to give a presentation on foundation models for neuroscience, and I was more than happy to do it because I already had a deck, so I didn't need to do any preparation. In actuality, I gave this presentation for the Brain Initiative, who are interested in essentially leveraging AI to accelerate neuroscience. So what are we talking about when we're talking about foundation models? First of all, this is not the right slide. Well, foundation models are large-scale models that many of you have had experience with. Of course, if you ever use Claude or ChatGPT, you have used a foundation model. I think in science, it's become very popular. Of course, the Nobel Prize was won in part by the team that implemented and built AlphaFold. We've also seen work, for instance, for universal cell embeddings, which is presented here. And now these kinds of models are used to generate different kinds of images and videos. So unfortunately, this video doesn't play because the translation from Google Drive to PowerPoint, but this is actually a video of puppies playing in the snow. It is delightful. It is completely a figment of the AI's imagination, and I highly recommend that you have a look at it. So what are foundation models? Well, these are models which are pre-trained in a self-supervised or unsupervised way. They're fine-tuned on downstream tasks. They're trained on large-scale data. They leverage large-scale compute, contain a large number of parameters. They use generic architectures with rather weak inductive biases, and their performance is predictable through scaling laws. They may display emergent properties which were not planned originally by the designers of these models. And finally, they are composable. So let's just go through a few of these. I'm not going to go through the entire list because I only have 40 minutes and now 35. All right, so pre-trained in a self-supervised way. So we have here a particular sentence, which is LLMs. We see the tokenization here. So the end of this word here is represented as this weird little token, which is #S. So LLMs are cool, and then essentially we train the model to predict what the next token might be. So in this case, it might be they are cool technology, they're cool beans, they're cool stuff. And if we train models at a large enough scale to be able to predict the next token, they learn something about the distribution of tokens in the real world. Now, to be able to do this, this kind of prediction at a large enough scale, you really do need to understand something about the world, right? Because there will come a time when the prediction task will be something about a fact within the world. Celine Dion is a singer, let's say, and so you will have to accumulate information about what the different actions or different facts about the world, and learning this kind of representation, this kind of distribution will eventually lead to a kind of statistical world model. When we're talking about large-scale data, I wanted to give a bit of a comparison because it's really hard to like even grasp like how big these models are. So this is La Recherche du Temps Perdu, Marcel Proust. If you ever want to spend an entire summer reading a book or a series of books, highly recommend it. It's probably like the longest book that anybody ever actually reads. It's I calculated it's about 2 million tokens, longest book, a single person's life work. So there's about 8 million times that book in the corpus of Llama, which is one of the largest open source model that currently exists, that was released by Meta. When we train large-scale models on these kinds of self-predictive, rather predictive losses at a large enough scale, they have predictable performance. So probably Irina was here a couple days ago, so I assume that she talked about scaling laws. Yes, yeah, of course. Okay, so so I'm sure that many of you are aware of scaling laws, so we can predict, essentially we fit different models at different sizes with different number of tokens, and then there's a clear relationship between the amount of compute that we put in, or for a fixed amount of compute, I should say, and what the validation loss is going to be, and we can use that to predict what is going to be the performance when we train the whole thing. And that's going to be very important because these are very large-scale kind of training runs that can cost millions and millions of dollars and involve very large-scale engineering efforts. So for instance, for Llama, there was 500 authors on the archive paper, so it's a lot of work, and the compute cost about $80 million. All right, so what about foundation models in neuroscience? So now we know everything that we need to know about large language models and those kinds of foundation models. I skipped no part. You know everything that there is to know. But what about foundation models in neuroscience? Well, there's a lot of papers that purport to train what might be deemed foundation models in neuroscience. So what do we have here? A foundation model for the mouse visual cortex, a foundation model for brain activity, a foundation model for animal behavior, a foundational model for intracranial neural signal decoding, and so on and so forth. So clearly, there's a lot of papers that are coming out. I have a whole spreadsheet, and I asked actually yesterday on Twitter on X, I should say, to update it. There's a paper that comes out seemingly every other day. And they're all kind of have different focuses. And so the question is, like, how do you categorize these things? How do you start thinking about, the possibilities that are brought about by these kinds of models? So I like this picture because I made it. So it's called, so this is an example of a mouse that's interacting with an environment. Okay, so there's the world, right? The world contains, in this case, water bottles and mazes and conspecifics, and the model, it's the real world, so it has its own dynamics. Now, the world gets projected on the inputs of the mouse. I'm not explaining this well, but I'm sure you understand what I'm trying to say here. So, for instance, the mouse sees photons detects photons from the outside world and creates and receives information about where things are located within the world via these projections. Now, so the inputs can include things like vision, can include audition, also proprioception. I'm going to count as potential inputs here. The inputs get integrated into the existing state of the brain. The brain is, its own dynamical system. Of course, Guillaume would be very happy to hear that. Yes, dynamical systems, positive. And so that nudges this dynamical system. From this dynamical system, we can read out either low-dimensional measurements, non-invasive measurements, which I'm calling NFT here, or we can measure these high-dimensional measurements, MFT, so for instance, using invasive electrophysiology. The state of the brain ultimately determines the outputs, so those are mostly going to be the positions of the muscles inside of the body of this animal, and that ultimately influences the world. So, if you wanted to virtualize a mouse, you would just need to take all of these 6 elements and just, do them virtually. But of course, what foundation models do is they focus on only parts of this graphical model. And generally, they mostly focus on pairwise aspects of this graphical model. So let's give a couple of examples. All right. So one possibility is to focus on that relationship between the inputs and the measurements, right? Up top here we have, we've probably seen this slide 4 or 5 times by my calculation. I just looked at other people's slides. I wasn't here for the last 2 days. Famous paper from Dan Yammans and Jim DiCarlo that looked at representations inside of convolutional neural networks, which are trained for image classification, and found that there was some relationship between the representations as well as representations which can be measured inside the brain. So generally, how this is going to work is we're going to take this this network, we're going to train a linear regression, essentially to go from latent representations of these networks onto that neural network, and generally we'll find a pretty good alignment, and definitely a better alignment than if we did this through simply going from the input. So that's the field of task-driven neural networks. An alternative, which has become more popular recently, is data-driven neural networks. So essentially we can take lots and lots of measurements now, let's say from mouse V1, and measure the relationship between the stimulus and the activity that we measure inside of this brain, and then essentially learn a digital twin, which is really just a CNN that's trained to predict the data here, and that can give us predictions. So the artifice here is very good if we don't have a lot of data and we just don't have so enough data to learn the number of parameters which we would need to fit a very complicated model. But these models have become more and more popular as we've had the ability to do larger scale recordings. I think you saw this. Again, I wasn't here yesterday, but I did steal this slide from yesterday's presenter. And one of the things that we can do with a model that goes from the input to measurement is to use it as a kind of digital twin that allows us to generate lots of stimuli, generate lots of data, and essentially probe it with any particular stimulus. But there are other kinds of models which have also been deemed foundation models. So here's one example. Basically, it's the same two things inside of this graphical model, but it's in this case we're going to go in the opposite direction. So we're going to try and back out from measurements what was the input that a particular animal was presented. In this case, the animal is a human inside of an MRI scanner. And they're presented with different videos, and the goal is to learn a function that allows us to decode what was it that was presented exactly to this person. Now, the models which allow us to generate images have been getting better and better. I don't need to tell you this if you ever use DALL-E or Midjourney and so on and so forth. Or Stable Diffusion, the models have been getting better, and the decoding models have also been getting better, so that, for instance, these are the scene images, and this was the state of the art here a couple of years ago, and now this is the current state of the art. So we can decode both the semantics and some of the details inside of these presented images using these large-scale models. Okay, so that's another kind of foundation model. A third kind of foundation model would be a model that just focuses on the output, or rather the behavior, and tracking this behavior. So I'm sure that many of you are aware of Deep Lab Cut, which is from Mackenzie Mattis's group that allows you to track different animals and different kinds of environments. So these models are trained on images at a large scale, so that the representations are relatively transferable from one circumstance to the other, and they allow tracking of behavior non-invasively. Here's yet another kind of foundation model that people have demonstrated. So we can go instead from measurements to what would be the output of the system. I see a lot of people, by the way, taking pictures so that they know the references. Don't worry, it's all on my blog post, so you don't need to do any of that. And I will give you the link after the fact. And I know that I speak fast, so that's why I write it down. Okay, so we have models that go from the measurements to the output. So most recently, there was this paper that demonstrated the ability to decode speech from speech motor cortex from a patient with ALS. So they had lost the ability to speak in a legible fashion. So we could, because of the loss of motor neurons and demyelination, I should say. But they still have good signals inside of their brain, so we can go inside of speech motor cortex and find a mapping between the representations inside of the brains and what they would have said. And so it's possible to both translate this neural activity from signals, this multi-unit activity, to phonemes, and it's also possible to generate speech through a voice box, which allows people to speak again. It's a truly magical technology. But I think that some of the most interesting possibilities are really coming from the fact that we have access to more and more measurements. And so models that really focus on just modeling the distribution of the data, whether it's non-invasive data or invasive data, are really becoming a lot more popular, and we'll hear a lot more about them throughout this set of presentations. Why these kinds of models? Well, first of all, learning a model through a self-supervised algorithm is rather straightforward. Every neuroscientist likes to use bespoke artisanal experimental paradigms, but the way that we record neurons is much more standardized because we have a certain number of probes which tend to be very popular. And so the raw data itself is easier to tackle and to learn from than the full parallel data streams. And there's a lot of data that exists online. So there's about 30,000 hours of intracortical EEG. There's about 10,000 hours of fMRI, about the same amount for local field potentials and spikes and so on and so forth. So if you add everything together, there's currently about 100,000 hours of freely available neural data online. And that is an incredible resource to learn a good representation of neural activity. So what would you do if you had a foundation model that was trained on representations that learn good representations of neural data? Well, you could use it as a kind of universal translator for neural activity. So you could take any kind of data, whether it's EEG, fMRI, calcium imaging, or electrophysiology, then train this neural foundation models using pre-training, using self-supervised learning, and then eventually fine-tune it for different downstream applications, some of which might include brain-computer interfaces, but you might also use it for psychiatric diagnoses or to evaluate what's the likely outcome of a clinical trial for a particular drug, and so on and so forth. So I'll give an illustrative example. I think that we'll probably cover this example also in Eva's keynote, which is going to be this afternoon, right? That's right. But anyways, it doesn't hurt to show it multiple times. So this is a recent paper. It got accepted in Neuroscience, actually. I heard from Cole yesterday. So it's called Towards a Universal Translator for Neural Dynamics at Single Cell, Single Spike Resolution. So what did they do here? Well, they took a lot of data from the International Brain Lab during a decision-making task. So they have data from hundreds of different areas using neuropixels, using a mouse that is doing different kinds of decision-making tasks. And so they get these parallel spike trains, right? So this is time, this is the number of neurons, and then they can decide to learn different kinds of representations using different kinds of masking scheme. So one kind of masking scheme is co-smoothing. So in other words, you take all of these spikes and then you say, I'm going to zap out all of the data from neuron 34 and neuron 10. And then the goal is to go from here and then predict back what was the activity in the neuron that were masked out. You could also do something like causal prediction. So you can take previous activity and try to predict what the activity is going to be in the future. You could do interregion prediction. So this is a variant of co-smoothing in which you zap out an entire region from the brain. Or you can do the same kind of thing that you do in task one, except that you mask out all of these other regions. So these are all variants of the same masking task that allow you to learn different types of representations or representations which are good at different things. Now, the way that they actually learn these representations is they chop up the data into thin slices. They use a linear transformation to map it onto a fixed dimensional space. And then they use a special token, a so-called prompt token, to say, oh, this is actually like one of these 4 tasks that you need to complete. And then they train this magic box, which is right here, which is a transformer model, in order to reconstruct the actual activity. So it's trained in a self-supervised manner. Now, the transformer itself is a variant of transformer which was proposed in 2022, which is the neural data transformer. So it's Joel Yee and Chetan Pandaranath who proposed this. So essentially, you take the spikes, you bend them, and that gives you a very tall kind of observation vector. You project that down to a fixed dimension. And then each of these thin slices, these short slices, I should say, of data, so I think it's 5 or 10 milliseconds, becomes a token, and then you get the tokens to interact with each other throughout all these layers, and then eventually you decode the information back out. And so lo and behold, we see scaling laws. So as you increase the number of sessions, you get better and better at doing these tasks, whether it's co-smoothing, forward prediction, intra-region prediction, or inter-region prediction. But what's more interesting is that you also get a little bit better at decoding downstream tasks, which were not part of the things that you originally trained on. So it's a form of representation learning. So you can do things like predict what was the choice that the mouse actually made, and you can predict things like what was the motion energy of the whiskers of that mouse during that task. And so that's the idea behind saying it could be a universal translator for neural dynamics. So you could take this one model, train it at scale to find good representations, and then use that for a bunch of different downstream tasks that were not planned. And right now, we tend to use very bespoke artisanal models to do our decoding. But I think that this is going to be a thing of the past in the recent future. I'll give you another example of what you might want to do with that. Actually, you know what? I'm not going to do it because you're going to talk, right? Okay, so I'm going to skip 2 slides and just close your eyes for a second while I go there rapidly because you're going to cover this. Okay, so I'll cover it. Great. One application for this is in BCI, so we can take data from a monkey that is moving a cursor on the screen using their arm. And so these are some of the traces from these monkeys, and we have data from their brains simultaneously. And we can train this kind of model on this data, find a good representation, and then we can take that representation that we learn and then transfer it to a different situation. So this different situation is going to be a handwriting task. And so the patient has to imagine that they're writing a particular letter. So this is for, again, an application for potential locked-in patient that wants to communicate with the outside world or that has paraplegia and wants to use their device. And so what we see is that if we try to decode this data from the human directly, we have a certain error rate, but we can take the representation that we learned from monkeys. Again, different species, different kind of recording technology, and then transfer it to this human, and actually it works pretty well. We can decrease the error by about 30%. And what's interesting is that you can enhance that still by using multi-session recordings in order to do the calibration, and you still get better than if you train from scratch on a human. So there is something about neurodynamics that is preserved between animals of different species. And that's the secret sauce behind all of these different foundation models. There's kind of a universal, representation or manifold that we can tap into, potentially, that will be determined over time. So in the following 14 minutes, we're gonna go through other kinds of results that people have demonstrated in the field. This is gonna be a whirlwind tour, and again, all of this is on my blog post, so you can click all of the links there. This is a paper that I really enjoyed. It's a paper that was trying to see if you could decode speech from EEG. Now, the conventional wisdom is that EEG is too poor, it's too low resolution in order to decode such a rich signal as EEG. It turns out that you can kind of do it if you train your model at a very large scale. So what they did is they had this poor, it was probably one of the experimenters, I should say, that did this. So they shaved this person's head, and then they had them in the lab speaking over a period of probably about 5 weeks, so 35 hours a week for 5 weeks. So 175 hours total of speaking inside the lab. I cannot think of a more boring way to spend 5 weeks. But they were able to demonstrate through that if you train these networks at a large enough scale, you can actually decode speech using EEG, which is truly remarkable. So they were able to, I think their hit rate, their top one error rate was 50%. Top one accuracy, I should say, was 50% when they trained on 175 hours of data. Now, what would be great is if this actually transferred between different people. They didn't have the resources in order to do that, and I think that in order to do this 175 hours, I don't know, like 1,000 people or something to find a good representation, that would require a tremendous amount of resources. But thankfully, our friends at Meta have done something that is, no, it's scalp EEG. But as you can see, if you just do 10 hours, which is a much more conventional kind, you don't even get to, I think you get to like 6%, right? So really this is only something that happens as you train for a very long time. Okay, so our friends at Meta did something that is conceptually related with much more resources. So what they have is an EMG, so electromyography band, and that allows you to measure the muscle activity inside of the wrist. And the goal was to decode different commands non-invasively. So I can do something like this in order to scroll up, scroll down, go right, go left, go right. And this could be a potential form of an interface for the purpose of augmented reality. Because if you had glasses that you had on your face and you were walking around in the world and you wanted to remove a notification for, let's say, you have like a big notification from Instagram, you're like, discard, discard. Ideally, you wouldn't want to be walking around all day just yelling at your glasses. You would want to be able to do this discreetly. And so that's the use case that they demonstrated. But to be clear, EMG is a form of neural data. It's just a form of peripheral neural data. And so the same kinds of lessons in terms of scaling do apply. So they were able to show that as you scaled up the number of participants up to, I think, 4,800 in one case and up to 6,500 in the other case, they were able to decrease the error rate for classification of different gestures down to 7% and down to 7% for Imagine, not Imagine, but for a kind of typing interface that they had. I should say that when you think about these 6,500 participants, this is about an hour of data from each of these people. So this is 6,500 hours of data in total. Obviously, like this would be very hard to collect for a single academic lab. But when we're talking about locations where they have these resources at industrial scale, they can get a lot more mileage out of what has been conventionally considered to be pretty noisy data. And here's a final example. I alluded to this most recently, in a slide about 20 slides ago. This paper from Paul Scotti and Tanishq Abraham that demonstrated decoding images from fMRI. So this paper is kind of interesting because they really threw the whole kitchen sink at the problem, right? So they have a shared latent space encoder that went from voxels to this common latent space, and they then used that as an input to a decoder, which is stable diffusion. So this is the XL version of stable diffusion, and they were able to use that to map from neural activity and eventually decode images from their brain. And so the important thing to notice here is that this stable diffusion decoder, it's something that already existed out in the world. Somebody else had, and I should say that somebody else is Stability, the company, had trained this neural network for the purpose of generating images, but they could use this pre-trained artifact that probably cost millions of dollars to train to decode neural activity. So it's really this kind of Lego block development, which I think is very appealing. The results, I think I presented before, but suffice it to say, it's become much better. Even in the last 2 years, there's been a tremendous improvement in the ability to decode images. But I should say that these things are not magic. Now, this is something that I think can kind of get lost in the weeds of this. It's like, wow, just like throw tons of data into like our little magic box, and then you just get whatever you want out of it. And that's absolutely not the case. The scaling laws are brutal, right? Because you need exponential increases in data in order to get linear improvements in the quality of decoding. And that depends on signal-to-noise ratio and the complexity of the signal, and ultimately it's an empirical question. So here's a paper that was much more sanguine, that was much less positive about this possibility. So it's a paper called Performance Reserves and Brain Imaging-Based Phenotype Prediction. And what they did is to try and predict person's psychiatric state or their age or their gender or whatever else. They had multiple questionnaires that they asked out of these people using the UK Biobank data. And so they went up to, I think, 40,000 or so participants, 46,197. It did not work very well. So so I want to zoom in. So this is their best case scenario, decoding sex from magnetic resonance imaging. They had 3 different kinds of MRI. They had the T1, they had the diffusion tensor imaging, and they also had a functional thing. And I think it's resting state functional MRI. Notice the x-axis here goes up to 10 to the 6, so they try to extrapolate what would be the performance if they had 1 million people to train their decoders on. And for sex and for age, it works kind of okay, but look at these, we can get this information using much simpler and less expensive means. So usually what we care about, if we care about biomarkers for psychiatry, is to decode things like, is a person depressed? Maybe we can get more information about their depression, or maybe it's a subtype or something. But I want to zoom in here. With a few hundred people inside of the data set, their depression, this is balanced accuracy. Their ability to detect depression was at 0.52, which is obviously terrible. And then it does inch up a little bit as they increase their sample size. And they predicted that if they had 10 to the 6 samples, so that's 1 million people inside of the data set, they could get up to 0.6. So that's 0.6 accuracy in decoding whether a person is depressed or not, according to this scale, when the alternative, now I should say 1 million people inside the scanner, just like do the mental math, right? It's about $1,000 an hour to do fMRI, to do an MRI scan. And so that's $1 billion that would be spent, potentially to do that. And it would have an accuracy which would be far lower than just asking a person, are you depressed or not? So it's very sad. No, it is, but these are empirical facts and we have to test them out, right? There's no way around it. And so these things are not magic. So my preliminary summary here is that, wow, there are many use cases for foundation models in neuroscience. Unsupervised learning can be quite scalable, and fine-tuning on small-scale downstream data, I think, can be very viable. And there are several impressive examples of neural decoding, but it's not magic. So the scaling laws have to be on one side. So with that, I have about 3 minutes left, and it's very early in the morning, so I'm going to give time for questions as well. Okay, so what now? Well, I think that I've seen a lot of attitudes here for this like brave new world of foundation models for neuroscience. I gave a similar talk, I think, in May, and Paul was in the room, and he said something to the effect of, Paul Szyzek said something to the effect of, this is mere engineering and it's not real science, which is, that's one way to do it. I'm not gonna argue with Paul. I love his work. If it's not your thing, if you don't want to do foundation models, don't do it. You absolutely don't need to. There's a different attitude, which is I cannot productively engage in foundation model research, but I think is a much more interesting kind of take, and I'll show some ideas about how you might be able to engage. And then there's cautious optimism. So when it comes to engaging in foundation model research, it does require a lot of resources. It requires resources for GPUs. It requires you to be knowledgeable about how to train models at scale. And so there was this recent paper, which I loved. I love the title, Choose Your Weapon, Survival Strategies for Depressed AI Academics. And the point that it made is there are ways to productively engage in large-scale AI research right now, but we have to be careful and about the ways in which we engage. So there are now ways to get access to the necessary compute. It's important to understand where in the ecosystem we lie, so that we don't try to battle the big companies on their own turf, because they will always win, right? So we have to do something that's slightly different, and that may be earlier in the pipeline, as opposed to doing the last mile, if you will, of translating this into the real world. I'll let you read this paper on your own time. It's delightful. But I think that another valid attitude is cautious optimism. So I'm a visual neuroscientist, so if I don't have a slide about Hubel and Weasel, I get fired from my job as a visual neuroscientist. So David Hubel famously, his first, I think, a big paper, I think this was a science paper, maybe it's a Nature paper, was on this new technical development, which was this thing called the tungsten microelectrode. So he was able to create a tungsten microelectrode, which is much harder than the previous ones that were used before. And with that, did the first recordings in primary visual cortex of cats, which ultimately led to all of this work that we now know about, that allowed us to understand visual cortex, and eventually led to his Nobel Prize in physiology. So the point is that if you have good tools, you might be able to find some new science, even though the goal might not be to create the tool itself. So I think that the best possible outcome with a tool like foundation models for neuroscience is eventually moving towards a kind of virtual neuroscience. So if we had virtual models of the brain inside of real brains, we could potentially have access to the entire state of the brain, such that it's reproducible, could do causal ablations, interventions, edits, such that there would be much less animals involved in research and would be faster. And I think that this kind of magical world of foundation models, like maybe it doesn't seem like we're anywhere close to that in mouse neuroscience or in human neuroscience, but I think in fly neuroscience, they're very close to that. So if you look at Nature. There was a recent special edition on Flywire. They published 10 different papers on the use of the connectomes to figure out what's going on inside of the fly brains. I highly recommend that you have a look through it. It was the edition like a week ago, or a couple of weeks ago. But it is truly astounding what they can do now that they have the whole brain connectome of flies. They can do things like virtualize flies and put them inside of virtual environments like Mujoko, and then figure out exactly what's going on inside the visual cortex using a combination of the connectome and task-driven neural networks. It's truly astounding. And so maybe with that kind of technology, with foundation models for neuroscience, we could build what I would call a Rosetta Stone for the brain. So something that allows us to build a universal translator for neural activity. And that would involve building large-scale training sets and stitching that data together. In order to do that, well, you would need to create large-scale science projects like the Enigma project or Leland Bio or First Neurotech, create both the technologies and the data sets in order to make it happen. So with that, I will conclude about my enthusiasm for foundation models for neuroscience, and I'll take questions. This is the blog post. It's on neuroai.science that has all the references and links and so on and so forth. Thank you very much.
Thank you, Patrick. We have time for a few questions, if there's any.
Yeah, thanks for the really inspiring talk. So it's very sobering as well for academics that are just at, let's say, public universities in North America. So do you think there's any fruitful direction that can make contact with these larger needs for huge amounts of compute? And so in academia as opposed to industry, what can we do? What should we do?
Definitely read this this opinion piece on strategies for people that want to engage in AI. I think they have some actual practical advice. The title is kind of a joke, but the information in that I think is quite reasonable. One way in which we can productively engage, for instance, is to look at neglected approaches in industry. It's important to understand, like, basically, what are the inputs and outputs in industry, right? So people are very expensive, but compute is relatively cheap. And so if there are things that would require a lot of people to like pore over, and it's very speculative, and there's a large chance that it doesn't work in the first place, then those are exactly the kinds of things that academics, I think, have an advantage over industry. So in other words, do things that are more speculative, that are kind of higher in terms of that are more speculative, that have less of a chance of actually working, and that require a lot of people to pore over data in a kind of manual fashion, and that are not industrializable.
So I think you left a lot of people out of the taxonomy of like opinions on foundation models. And one thing, I think I've met a lot of people who are not cautiously optimistic, for one. And I think there's another group that you didn't mention, which includes people who are concerned about like the carbon emissions and the amount of resources being poured into foundation models. You didn't mention anything about that throughout the talk, so I was curious whether you think it's not something we should be concerned about, or that like it'll just be solved based on, I don't know. What are your thoughts on that?
I think I was not able to find like an hexagon that would allow me to put all the different labels, but I was specifically thinking about Paul Chiswick when I was putting that one item in that corner of the triangle. But you're right. I think like a lot of people are concerned about ethics now, and people are concerned about ethics in the long term. I work in AI safety now, and people are very much concerned about stuff that's going to happen in 7 to 10 years. I think that with respect to, I think we can do the back of the envelope when it comes to carbon emissions. And I think that Miele did this exercise a couple of years ago for their own cluster and came to the conclusion that it was something, and maybe I'm speaking out of turn here, but it was something like 50 or 100 tons of emissions, tons of carbon dioxide equivalent per year, which would be the equivalent of 5 to 10 North American households. So all in all, a pretty small amount compared to the size of the amount of research which is being created. It's really when these things scale up that that I think the carbon emissions really start to matter. But there are...
Is that specifically for neuroscience research at Miele, or is that for...
No, that's for all of Miele. I was shocked actually when I saw the numbers. I was like, "What? This seems like really tiny, especially compared to." So I also did the same thing for a conference like SFN. So I was involved in NeuroMatch for a long time, and we were trying to estimate what was the carbon impact of creating NeuroMatch, where we're creating these virtual conferences and virtual summer schools rather than the real thing, and that was way larger than the compute that then came into these things. Because if you just fly 20 people across the Atlantic Ocean, I mean, you're at something that's closer to that. It might not be 20, it might be 50, but it really doesn't take a whole lot of people. So I do think that, same idea as with scaling laws, the numbers really do matter. We can talk about this in kind of abstract terms, but I think we need to do the math and figure out whether these things are actually worth it.
Yeah,
So.
I mean, I've seen numbers.
But to be clear, I do want to add one thing there, which is that we do not know the embodied carbon that comes inside the GPUs, and that's something that Sasha Lucioni has mentioned many times. We don't know. NVIDIA doesn't tell us like what is the embodied carbon that goes inside of a H100. So that might be the iceberg. Maybe it's 10 times larger. We don't know.
Okay, I'm looking forward to discussing more with you.
Awesome.
Maybe one last question from Zeke, and then...
Yeah, so a quick question, but first actually, just to add to the last fantastic question about carbon emissions, there's a really great podcast where actually Miele's own Sasha Lucioni, who does a lot of...
The same person I was just mentioning a second ago, yes.
Yeah.
We're talking about the same person, yes.
Honestly, I just recommend looking up her Google Scholar because she looks into this a lot. And one important thing to think about is that Miele runs its cluster on Quebec's like very clean kind of hydroelectricity grid. So Miele has pretty low carbon emissions because of running it off like hydropower. But one thing to take into consider with these models is actually going beyond just the carbon emissions and looking at the kind of net energy that they consume, because usually the energy that they consume is quite high, and a lot of times this is energy that's being rerouted from other really kind of important areas of society.
Yeah, but in Quebec, we give these contracts for almost free hydro for these large-scale industries because we want aluminum to be cheap in Lac Saint-Jean, right? So I think that we have to think about these things at a larger scale than just like this one particular thing. We have to look in. Like I don't agree that we should have it so that's like 5.7 cents for Adcan in Saguenay-Lac-Saint-Jean to make lots of aluminum for very cheap. So if we can use this energy in the most efficient way possible, I think it makes a lot more sense. But from an individual household perspective in Quebec, we use so much electricity because we've just become accustomed to this fact that electricity is too cheap to meter, and it is truly a bad thing for the environment, for all of us. So I think we're in kind of the funny money kind of mindset when it comes to these things. Anyways, we can have a much longer discussion about this.
For sure. So I guess
yes.
just the other question that I wanted to ask if we have a moment is, I know with a lot of other, and stop me if you already answered this right at the start because I unfortunately missed the start of your super cool talk. But I guess thinking about other foundation models, one thing that people talk about a lot is perhaps the kind of misappropriately named like hallucinations, and having things like appear that I mean, like the classic kind of ChatGPT thing that gives you the number of rocks that you want on your pizza if you ask it how many rocks to bake into your pizza. Would you see something, do you think there's a kind of worry for having hallucinations in Neuroscience Foundation models that end up potentially leading to like papers being published on stuff that really isn't there?
Yeah, yeah, of course. That can happen. And to be clear, when I was talking about the applications in psychiatry in general, I think we have to be very careful about applying these kinds of models for human research, because misclassifications have, or hallucinations, if you want to call them. I mean, what is what is an hallucination but a kind of misclassification in long form? I think these things can have very negative consequences for people. But I'm more interested in, and I do kind of a large coverage here, but I'm more interested in applications for either for basic science or for things that don't really have to do with health, like they're more about uses of brain-computer interfaces for natural interfaces, so which I think is less problematic. But yes, I hear you.
Yeah. So we'll ask Matt to plug in, and while this switch is happening, maybe I can follow up on one little point for you, Patrick, is, you know, to Zeke's point about hallucination, I think one of the biggest questions about foundation models is your proposed application as digital substrate or like digital brains, right?
Yeah.
Because this use case would essentially ask generalization properties of these models.
Yes.
In the sense that you fit the model to whatever you can, and then you ask novel questions about it. And so
You need causal data in order to do this in the most general sense. You would need causal data.
Yeah.
Yeah.
And so the question for you is, do you know of anybody doing specifically generalization research in these types of neuroscience-based models? It seems like these questions are there in language models and so on and so forth, but it seemed like that's the next place to go if you want to go towards digital brains. And I'd like to hear what you think about this.
Yes, people are care a lot about about this problem, but it's very early days still. But we can talk offline, and also we have the panel, and so I don't want to take too much time from
That's
from
true.
Matt.
Yeah. Don't worry, we baked in some extra time, so we're actually quite on schedule right now. So